Hello, everybody. Welcome back to the YouTube channel, my YouTube channel here. My name is Masoud Olia, and I'm a professor in School of Engineering at Wentworth University. And I'm here with another example. This time I'm looking at a problem where it's related to the topic of axially loaded members, the subject of mechanics of materials. And I noticed that the video that I had made before uh, had many viewers and people were interested. And I thought maybe I should do another example of this problem and just remind you about the video that is available to you as well. So I just want to remind you, and I would put the link actually in the bottom of this newly posted video on YouTube to remind you about the link for those people who haven't seen the video. So I'm talking about this video that I had put some times ago on 2019. And this is, I'm just going to fast forward this to show you the equation. So basically, you have an axially loaded members, right? And this is a rectangular block. And then you wanted to find the stresses that are developed on an incline. And this is obviously important in situations when we are pieces that are bonded together at an angle, or for like natural blocks of wood where the grain is not, necessarily along the axis, and it's along some angle. So I went through this video and I showed you how you can actually figure out the normal and shear stresses that are developed on that plane. So again, as I said, I would put the link there. And I want to get to the equations actually. So just remind you that the area here is the area of the initial cross-sectional area, not the area of the incline, which is much larger, depending on the angle, of course. So eventually, if we fast forward this, we get the two equations. The equations for sigma at that plane, I call it sigma sub theta, and the tau at that plane. Okay, so you can see the equation. Sigma sub theta is P over A sine square theta. And tau sub A, you could write it actually in terms of sine 2 theta, or you can just have it as sine theta, cosine theta. Okay, so let me go back now, and we'll go back to this screen. So let's say we have a load of 500 pounds, just as an example, right? And now you got to be careful, guys. The angle that I had in the problem was this one. So you see, we are given this angle, 60 degrees. We want to know what's going on this plane here. In other words, what stresses are developed on this plane. So in other words, if you draw a free body diagram, or I should say a stress diagram of this section, this angle actually is 30 degrees. Your theta is 30 degrees. And our objective is to find what the stresses are developed here due to this load. See, this is the applied load, the 500 pound. And we want to know what is, sorry for this, sigma sub theta and tau sub theta. Okay, and look, the area that we are talking about is this area, this cross-sectional area here, the 0.5 by 1.75, right? So let me go ahead and calculate that area for you. So the area is 1/2 inch by 1.75 inch. So that becomes 0.875, I believe. Yeah, inches squared. So our objective is to find the stresses on that incline. So just a reminder, guys, that again, I want to go back to this picture here, and you see the angle, the way it was defined. Let's go back. You see the angle theta is that angle. So in this picture, by mistake, some people would use the 60 degrees. The angle is 30 degrees. So the formulas, you guys remember now, sigma sub theta was what? P over A sine square theta So go ahead, plug in the information you have. 500 pound divided by 0.875 inches squared. So that's pound per inch squared PSI times sine square of 30 degrees. So if you do the calculations for this one, this should come out to be about 142.86 units should be PSI. So that would be this guy here, the stress developed on that plane. And then similarly, tau sub theta is, you could use the P over A sine theta cosine theta, or use the trig identity and use P over 2A sine double angle. So again, 500 divided by 2 times the area, you know the unit is good. And then this would be sine of 2 theta, 2 times 30 degree becomes 60 degrees. So if you do the calculations here, you get 247.43 psi. So this was just a short video, just an example, and the confusion on the angle some people have. And I've seen that when I teach this course, always people say, oh, which angle should I use? Well, you got to go back and see how you develop the equations. Okay, so as usual, I'd appreciate if you like the video and subscribe if you want to see new videos. And I would put the link of the video that I just showed you, just in case for those people who want to go back and see the derivation. And in that video, actually, I do talk about the importance of the fact that maximum shear stress, this guy, happens at 45-degree angle for an axially loaded member. And that's very important in design, because ductile materials, as I mentioned in that video, the mode of failure is shear. And if you just pull something in the axial direction, right, and if that material is ductile, because the mode of failure is shear, maximum shear stress happens at 45 degrees. You'll see a 45-degree break line. Okay, so thank you, and I'll see you soon.